Mathematics, featuring lecturer Beatrice Lumpkin, retired professor from Malcolm X College of Chicago, and Peggy Lipschitz, artist. This is one in a series of African-American baseline essay presentations produced by Portland Public Schools' Multicultural, Multi-Ethnic Education Office.
Welcome to our talk on the African roots of mathematics. Most of the mathematics that we teach in elementary and high school comes to us from Africa. Africa was the birthplace of the human race. From Africa, people spread all over the world, taking with them language and the concept of numbers. We know that mathematics was born in Africa because every language has words for numbers and the logic of mathematics. And wherever there are people, there are numbers. What's that, Peggy?
This is the stork bringing the human race to Africa. There she is, counting her fingers, little feet hanging out in the back, little hair on her head.
Yes, we know that Africans could count tens of thousands of years ago, and the proof is written in stone, or at least in fossils, from the interior of Africa, the central Congo region. We have found a bone that was carved by the Ashango people about 8,000 BC. And on this bone, there are notches that are very interesting because we see
3, and 6, then 4, then 8.
Well, that looks like multiplication by 2.
But then it fools you. It has 10, and 5, and then 5, and 7.
Now, on the other side, there are notches that represent prime numbers, starting with 11.
That's right. 13, 17, and 19. Too many to draw them all.
Now, there are some scholars who believe this was a record of phases of the moon, an early calendar. We don't know the purpose, but we do have proof. Numbers were recorded in Africa 10,000 years ago. And now we'll move upward in time elsewhere in Africa, in the Nile River Valley. A rich Nile River Valley, and still about 5,000 years before the present time, where an African people built a high civilization, invented agriculture, and we think women invented agriculture because it was the women who were the food gatherers. The ancient Egyptians built pyramids, temples, and in order to assure good crops, since it almost never rained in Egypt, irrigation was needed. A central government, kings, queens, poets, and mathematicians. Mathematicians.
Here comes the fields, wheat and barley, all different shapes. And here at the edge, when the floods didn't come past a certain point, the desert around the edges. That's why they needed to irrigate it. These rough mountains in the back.
Now the numbers they wrote, the numerals they wrote, look somewhat different from those ancient ones from the Congo. How did they do it?
They did it with strokes, like 1 would be 1 stroke, 2, 2, 3, 4, all the way up to 9.
Now that's like the Ashango bone, but here we take a big step in history, not on the moon, but instead of a 10th stroke, we have a symbol for 10, the first cipher in history, and base 10.
And it went
From
on.
here,
10, 11, 12, like this. They could also write 12 the other way, like this, from right to left.
now we couldn't do that, could we? Because we would have 12 not equal to 21. But their system of numerals were additive. Usually they did it this way, writing from right to left as ancient and modern Hebrews and Arabs do to this day.
Then they had symbols for all the other big numbers, like 100 was a coil like this, 1,000 was a lotus blossom, a little flower in a flower pot. It's 1,000. 10,000 was a little fish.
Definitely more beautiful than our numbers.
100,000 was a tadpole with a little leg. And 1,000,000 was really, it was somebody hitting the jackpot. It was a little fellow going, wow, like this. That's how they wrote 1,000,000. This one is 100,000.
Yes, there was so much to learn in ancient Egypt that many schools had to be opened for the scribes. There's a wonderful story about an Egyptian boy born in Nubia who became a famous mathematician and engineer. We'll call him Senefer, and he makes a great role model for our students. Senefer was the son of a carpenter who won a scholarship to go to school because of his genius in mathematics. He learned how to write his numerals in the marketplace watching the scribes. And in fact, he taught himself how to add. But it was easy with Egyptian numerals. Suppose we added 24 and 38.
24.
What would that be?
Well, 24 and 38. Senefer would have written, for 24 he would have had 2 loops, that's 20, and 4 strokes. And for 38 he would have 3 hoops and 8 strokes. 1, 2, 3, 4, 5, 6, 7, 8. Then to add them up,
Let's take one of those out.
I got too many. Cancel one. Cancel this one. 8. Okay, so then he'd add them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And he would write it a 10 and 2 strokes. And then all he had to do was count up these 10 hoops. 1, 2, 3, 4, 5, and bring them down here. 1, 2, 3, 4, 5. And there he would have his answer. 6 hoops and 2 of these. Very close to what we would get if we just added this together. Like this. 62.
And he didn't have to memorize that 4 and 8 were 12 because all he did was count. Multiplication was also easy with Egyptian numerals. Suppose we look at 35 times 13. The Egyptians knew it was easier to multiply by 13, and they used the commutative property of multiplication to change that to 13 times 35. Again, they didn't need to memorize tables. They used the process of doubling, starting with 135, and then we're going to double that with 2 35s, 35 and 35.
70. Then double it again. Add another 70 to 70. It's 140. And then double it again. Add another 4. You got 8 35s. 280. Now
Would you want to double that again?
Well, you don't want 16 because all we're looking for is 13. So here's the way they did it. They built themselves to 13. They said, well, here's 8. We'll take our 8 35s over here, 280. Then we'll take our 4 35s, 140. And that gives us 12 of them, so we just need one more. Take our 135, it's 35. And here we've got 13 of them. And then just add them up. 5, 4.
And actually, they were using the same principle of the distributive property of multiplication that we use today.
Because we would multiply by the 3 and get 105, and then we'd multiply by the 1, which is 10, put it over here. Whoop, 5. Getting a little too fast here. And again, get the same answer.
But with the Egyptian method, students don't have to memorize tables, just how to add. Egyptian mathematics specialized in fractions. Suppose you wanted to measure a wall or this length of paper using your forearm, which the Egyptians called a cubit. 1 cubit. But a wall would not measure exactly an exact number of cubits, and fractions were needed. Fractions were also needed in order to divide provisions among a large work crew. And so the Egyptians invented unit fractions, which we are showing, by using an operator symbol, the very first in history. This is the Egyptian letter R, and it means invert.
Oh, it's an open mouth, isn't that right?
Yes, that's right.
So we'll have it talking, saying invert. Makes it easy.
Invert me. We'll start with 1/3.
Okay. A third would be the open mouth with 3 strokes underneath. What else will it have?
1/4.
1/4. Like this. I'll mark what they are.
And let's look at 1/20.
1/20 would be the mouth over 2 hoops.
They also added fractions using a concept like the least common denominator. Egyptians also invented algebra because they needed to solve problems leading to first and second degrees. But they called their unknown aha, or aha. We'll just call it X. Suppose you had a problem 1/7 of aha plus aha, which we're calling X, equals 32. What is aha? Well, the method they used was false position. Assume some value for X, a convenient one, 7. Does it equal 7? Try it. What will we get?
We'll get
1/7 of 7
7 plus 7
equals 32?
No.
Not
Sorry,
really.
it's 8.
But it should have been 32. Now, if we multiply 8 by 4, that would be correct. So let's go back to the X equals 7, correct it by multiplying by 4. Try X equals 28. And once the proof by substituting,
That
and
gives
we'll
us
close the parentheses there, around the 28. 1/7 of 28, 4, plus 28 does give us 32. And this method was used up until the 20th century. You can still find it in American textbooks of that period. And it comes to us from ancient Egypt. And we're very pleased indeed to find another way to solve our equations and to know that it comes from Africa. So all of this mathematics was needed for the huge projects that the Egyptians planned. Geometry was one of the first sciences because the Nile River covered all the boundaries when it overflowed. Well, the farms were different shapes because the river zigzagged. Some were triangles, and what did they find the area of a
They found
triangle
the area,
to be?
they found it was half of
The base times the
times
height.
the height.
Same formula we use today. For trapezoids,
Trapezoids,
they took,
Again, here's the height.
again, they
Two
need the
bases.
height.
Base 1, base 2,
And the area then will be a half, the sum of the bases times the height, the very formula we use today. But it was in the area of a circle that Egyptian mathematics reached a high point, because to measure area of circle with square measure is a challenge. They took the diameter, as we would, 8/9 of the diameter, and said square it. That gave them a square of area 99% close to what we find today, 8/9 the diameter squared. Comparing it with our formula for area equals pi r squared gives a value of pi equal to 3.16. 99% accuracy, even more accurate than the biblical value of 3, which was 95% accurate. And so with the algebra and the geometry, they were able to do great things like plan the building of temples and huge obelisks. Queen Hatshepsut sent 10,000 people a distance of hundreds of miles up the Nile River just to bring the stone from Aswan. How much food would it take? Fuel, clothing, books. For a 7-month trip, 33 ships set out. Even today, that would be a lot of calculation, a lot of mathematics.
Here's the great big stone. They built a kind of a sled underneath it. Then they put all these logs that I put in here under to kind of help it to roll along.
That's
And
really the hardest job, is dragging that stone up to the temple. It certainly took teamwork.
these people, as the logs fell out of the back, they had to run up to the front and put them in again underneath. There was always a little person sitting up here putting some kind of lubricant onto the ground underneath. And from all of these ropes that are keeping it, people were pulling. And from the front, people were pulling, hundreds of people
And they
pulling.
didn't step on each other's toes. Now that's what you call planning.
All people, every one of them. There we go, pulling and pulling. So it was a tremendous load, pulling all this thing up the hill. And of course they had to worry about the food, a little refreshment for them, keeping the pots boiling, and getting the next group ready to come on.
In fact, they were well fed. They weren't slaves. Forget the Egyptian stereotypes from Hollywood. They were free farmers who were working while the fields were flooded for wages. And when we finished, what are we going to do? A great big party. Those obelisks still stand to this day, a monument to the ancient African engineers. Now, it was the woman who had ordered these great obelisks. Queen Hatshepsut had done what no man before her had done. Among her great works were rebuilding Egypt with an era of prosperity and peace, because Egypt was just recovering from invasions. Many schools were opened. Poets wrote love poems. Culture blossomed because Hatshepsut's reign was an era of peace. And among some of her other great works were sending a fleet to the famed land of Punt, mentioned in the Bible, going hundreds of miles down the Red Sea, around the Horn of Africa, bringing back to Egypt gold, jewels, leopard skins, and incense. And under Queen Hatshepsut, the most beautiful temple still standing in Egypt today was built by her design. And so she began to think, I've done more than any man before me. Why just be the queen? Where is it written that a woman cannot be pharaoh? And only the pharaoh had unlimited power. So Hatshepsut had a vision. And she saw the god Amen telling her, you are my very own child, and I name you the pharaoh. But what would it take? She did it without surgery. How did she do it, Pagan?
Well, she took the flail, which was the symbol of power, and the other one, the stick, and then she put on the double helmet of Egypt, the double one of Upper and Lower Egypt. One of them was red. And then she put on the beard. Here comes the beard. She strapped it on. It was a ritual beard anyway, a golden one, even when the men wore it. So here she is with her golden beard.
And so she became the pharaoh. Many other African countries were ruled by women. Even after the Greeks invaded Egypt, mathematics continued in the African tradition. Only the language changed. Just as today many Asian or African scholars write in English, the Egyptian scholars began to write in the Greek language. Now, Hypatia was a famous mathematician, an Egyptian woman, using the Greek letters for the numbers. Now, that was harder than adding Egyptian hieroglyphs, but she was a brilliant algebraist, and it gave her no problem. She was a professor at the University of Alexandria, but a terrible thing happened. Alexandria was the scene of riots by mobs of fanatic Christians who murdered her and dismembered her. A terrible thing. But we should remember her not as a martyr only, but for the contribution that she made to science and mathematics. A later invasion of Egypt also found Egyptian mathematics continuing, but now they wrote in Arabic. And among the gifts of Africa are the numerals we use today, which are the Arabic numerals and came to us from North Africa. We see Abu Kamil. All of his work was copied word for word by Fibonacci of Italy. We should remember the original great mathematician from North Africa, from Egypt, Abu Kamil. He taught us how to solve complicated equations that go well beyond what we teach in high school today. Traditional mathematics, or that tradition, continued even after Africa was devastated by the slave raids and invasions. Today in Mozambique, peasants, in fact, who have never gone to school, build their rectangular houses according to an advanced geometric principle. What do? They
take two ropes and they knot them together at the center of each rope. And they put one end of each into the ground, and then they get the ropes and they pull on them, straightening them out. And when they get them straightened out, they have a perfect rectangle.
Now, as we know, that will give us a perfect rectangle. And elsewhere, children in Angola, elsewhere in Africa, play a mathematical game where they trace a figure like this, never lifting up their pencil and never retracing a line. Now, if you want the full explanation of this game, read your baseline essay. We can think of mathematics as a tree that's rooted in ancient Africa, a large root coming from Africa, another one from Asia. Don't forget the Native American root, because they were the first to invent a symbol for zero. And the tree today is blooming all over the world. In the United States, black mathematicians continue this African tradition. They are working in the mathematics of computers, medicine, space travel. And let's put a dove at the top of the tree, because we need peace for the tree of mathematics to continue to develop, and so that its fruits can be enjoyed by the children of generations yet to come. Now we'd be very happy to entertain any questions.
The concept of zero, you said, was developed by the American Indians. What did they do for zero before the new continent was discovered?
Well, as you noticed, in Egyptian mathematics, a zero was not needed because that system did not use place value. A symbol for zero wasn't needed. In other systems, they left a space, but that wasn't too good because it created a lot of ambiguity. The zero that came to us actually also came through Africa, but it was first used and developed by the people of India about the year 900. And so you see, little by little, with people participating in Asia, Africa, Europe, and the Americas, our science of mathematics was built.
Would you recommend one book that a primary teacher could read to get started with all of this information? Is there a best book that you would recommend?
There are quite a few books. In fact, Peggy and I did the book that you will be receiving for high school level, but we also have a manual for teachers that goes a bit more in depth. Our thinking was that this story of mathematics is best told as a story, so that it can be seen in the context of the needs of the people of that time. We wanted our students to see mathematics as a living subject and as a human subject. This helps put them at ease. Rather than just showing, well, this is how the Egyptians did their multiplication, if they see it as a development, they can begin to think of mathematics in a different way. And so I'm very happy that you will be reading Senefer and Hatshepsut, but in addition, for those who want to tackle it more deeply, there is a book by Richard J. Gillings called Mathematics in the Time of the Pharaohs, which is the most definitive work in this field.
I found that your information was very interesting, and I was wondering from what source or where did you compile most of that information?
I should credit my students at Malcolm X College for starting me in the study, because they were demanding relevance in education. If you remember, in the late 60s, teaching mathematics, I had been taught that mathematics is eternal, and I hadn't thought of it as having a history. But going back into the history of Egypt, I found that indeed they knew a great deal of mathematics then. And so I started with the standard textbooks, histories of mathematics. But I was also dismayed at the way these histories disparaged the contributions of these ancient peoples. After going through all of the standard histories, I looked at books like W.E. Du Bois, The World in Africa, which gave me a different insight. So I had to go beyond mathematics to begin to accumulate this material. Then the book by Gillings that I mentioned is a real pioneering study. More recent textbooks, such as Carl Boyer's The History of Mathematics, have shed a great deal of the prejudice of the past, and that book also makes an excellent reference. Other than that, there are professional journals, such as Historia Mathematica. If you go through their back issues, there's a lot of material, and I'll be so happy if you yourself would like to look more deeply into this. Peggy and I are looking for the next generation to take over this very vital study. Please see me, and I'll be happy to talk at length.
Dr. Lumpkin, I could think of reasons for myself, but what I see is maybe most elementary teachers that teach math is the kind of thing, you know, you just teach the formula, how to get the answer, and that's it. People don't see the validity of teaching the history behind that. And so what is the number one thing that you would tell just an elementary teacher that is not used to doing this? What is the number one reason for teaching this history?
Well, number one, I would say it would, the use of history in teaching mathematics humanizes a subject. Many students come in already traumatized into the mathematics classroom. Even at the college level, I would start any math class by asking students to think, what is mathematics? And often they will say, well, it uses numbers. What were the first numbers? Why did people need numbers? Now, no matter how backwards a student feels she or he is in mathematics, they can think about why did people need numbers, and that puts them at ease. So it helps bring the students over to the teacher's side. That is the number one thing. Then also in combating prejudice, I think it's very liberating to realize that mathematics is a product not only of modern Europe, but had its roots in Africa. So I would say there are several reasons to humanize the subject, to set the students at ease. When they realize how many thousands of years it took mathematicians, for example, to develop that system of multiplication or division, then a student feels more patient if they don't learn it the first day and realize the human race took thousands of years to develop it.
On the drawing, you had the symbol 12 going both right and left. And did they have problems with that? And when did they change to go in one direction, such as the Roman numerals?
It was no problem for them because the numbers were additive. And they were so artistic that there were times when they would, on their monuments, write the number vertically, top going down or bottom going up. In terms of the place value system that we use today, that was developed, as I mentioned during our presentation, basically developed in Asia, moved into Africa, and brought to us in Europe. That was about, actually, I would say about from 700 AD to 900 AD. that that development took place. Now, incidentally, our modern method of multiplication also came from Africa. It was brought by the Moors into Venice. And from there, the Hindu-Arabic numerals competed with the Roman numerals. Well, a law was passed that the new numbers could not be used. There were riots over that subject. But as is always the case, eventually, the more progressive form won out. So we can see this has been a long development, and we still have a lot further to go.
In our curriculums, we are moving away from piecemealing everything. And it's such a beautiful harmony of subject areas that you've pulled together in math. You've brought out so many things. I thank you for that.
Thank you. And if we ever get the chance to do a similar presentation, perhaps for the upper grades, we have come to the realization that music should also be brought into this. And I agree with you that it's much more humanistic to teach these subjects as they relate to each other and not in a cold, hard, isolated way. Thank you.